In this video, we're going to perform a goodness of fit test for the Poisson distribution. The first step is to set up the null and alternative hypotheses. The null hypothesis is the population has a Poisson probability distribution. The alternative is the population does not have a Poisson distribution. Next, we're going to select a random sample and record observed frequencies for each value of the Poisson random variable. Then we'll use this information to compute an estimate of the mean number of occurrences. Now, because we don't know what the true mean is, we're going to use the sample mean. So therefore, the estimated parameters in this test equals 1. So the degrees of freedom for this test will be the number of categories minus 1 minus 1. Then we're going to compute the expected frequencies for each value of the Poisson random variable. The Poisson probability distribution is given by this equation, mu to the x, e to the minus mu divided by x factorial. Note that x factorial equals 1 if x equals 0, equals 1 if x is equal to 1, equals 2 if x is equal to 2, because 2 times 1 is 2, equals 6 if x is equal to 3, because 3 times 2 times 1 is 6, etc., etc. Now we're going to use this equation to compute these probabilities. And we'll take these probabilities and multiply by the sample size. Next, we're going to compute the values of the test statistic, and with every goodness of fit test, we do the same exact thing over and over and over. We take observed frequencies, we subtract off the expected frequency, we square those deviations, and then we divide by what we expect, and we sum them up. Now, K is the number of categories, and then we're going to use the critical value approach to this test. So we're going to reject the null hypothesis if chi-square stat is larger than its critical value. Now, the intuition behind this test is if what we observe is close to what we expect, which is based on the Poisson distribution, then these k differences are going to be really close to 0. If the observed frequencies are exactly equal to what we expect, then each of these k deviations from expected is 0. And therefore the chi-square stat is 0. Now if the observed frequencies are much different than what we expect, then those deviations are going to be large. Squaring those large deviations is going to give us an even larger number, which means the chi-square stat will be very, very, very large. So as the chi-square stat gets closer and closer and closer and closer to 0, there's more and more and more evidence in support of the null hypothesis that the underlying distribution is Poisson. Alpha is the significance level, and the degrees of freedom are k minus p minus 1, where p is the number of parameters estimated. Now remember that in a Poisson, the mean and the variance are both equal, which is represented by the mu in this equation. And we don't know what mu is, so we use an estimate of it from the sample. Now in our example here, we're looking at a parking garage. In studying the need for an additional entrance to a city parking garage, a consultant has recommended an analysis approach that is applicable only in situations where the number of cars entering during a specific time period follows a Poisson distribution. A random sample of n equal 100 1-minute time intervals resulted in the customer arrivals listed below. A statistical test must be conducted to see if the assumption of a Poisson distribution is reasonable. Okay, so here we're counting up the number of times in a 1-minute interval that 0 cars showed up during that 1 minute time interval. And according to the sample data, that occurred 0 times. Next, we want to count up how many times 1 car arrived in a 1 minute interval. And that happened 1 times. And then we want to count up the number of times 2 cars showed up in the 1 minute interval. And that happened 4 times. 3 cars showing up in 1 minute intervals happened 10 times. 4 cars showing up in 1 minute intervals happened 14 times, etc., etc., etc. Now this right here adds up to 100. The hypothesis is number of cars entering the garage during a 1 minute interval is Poisson distributed. The alternative hypothesis is number of cars entering the garage during a 1 minute interval is not Poisson distributed. So we need to estimate the Poisson probability function, which means we have to calculate the mean of X cars arriving. So what we do here is we take this right here, the 0 here is 0 cars in a 1 minute time interval. And that happened 0 times. Okay. Then we add to that how many times 1 car pulled up to the garage in a 1 minute time interval. And that happened once. And then we look at 2 cars in a 1 minute interval, which happened 4 times. And then 3 cars entering the parking garage during a 1 minute time interval. That occurred 10 times. And we do that for all values of X, with the last one being 12 cars entering the garage in a 1 minute time interval, which only happened once. Note, the numbers in red here are the observed frequencies, while the numbers in black here represent how many cars were in each 1 minute time interval. So basically all we're doing is we're taking 0 times 0 plus 1 times 1 plus 2 times 4 plus 3 times 10 plus 4 times 14 plus etc., etc., etc. plus 11 times 3 plus 12 times 1, which equals 600. And when we compute that, we get 600 total cars. Now, how many 1 minute intervals did we add? We had 100, so N is 100. These red numbers, again, are the frequencies. So we're essentially adding up the red numbers here to get us to N. And the sum of these red numbers is 100 because we had 100 1 minute time intervals. So the mean is basically take each of these numbers, multiply by each one of these numbers, the corresponding number here, sum that up, and then divide that by the sum of the red numbers. The sum of the red frequencies, observed frequencies, is 100. The estimate of mu is 600 cars divided by 100 1 minute intervals. So we have 6 cars arriving every minute on average. Hence, to hypothesize probability of X cars arriving during the time interval is, now this is true if the underlying distribution is Poisson. F of X equals 6 to the X times e to the minus 6 divided by X factorial. So we're computing probabilities based on the assumption that the distribution is in fact Poisson. Now we need to compute the expected frequencies. First, we have to compute the probabilities for every value of X. So for X equals 0, we plug in 0 for X. 6 to the 0 is 1. 0 factorial is 1. So f to the 0 is just e to the minus 6, which is 0.0025 approximately. Okay. Now for x equal 1, we plug in 1 for x, 6 to the 1, divided by 1 factorial, times e to the minus 6 is 0.0149. The rest of the probabilities are computed in a similar way. Now, I should note here that this probability here was found by adding up these probabilities and all of these probabilities to x equal 11. After adding these probabilities up, I subtract that total from 1, which gives me this. Because the Poisson distribution, there is no limit to x. The probability will fall and get closer and closer and closer to 0 as x gets larger and larger and larger. But we only had x equal 12 in our sample. So when we compute the probability of x equal 12, we have to calculate the probability that x equals or is greater than 12. Hence the 12 plus here. So when I add up this column of f of x's, I get 1. Now, I got 0.25 here because, remember, n is 100, and 100 times 0.0025 is 0.25. 100 times this number is 1.49. 100 times that number is 4.46, etc., etc., etc. Now, again, when I add up this column here, I get 1, because remember, this is the probability. This right here is the probability that x is equal to 12 or greater than 12. When I sum up the last column, I get 100. The expected frequencies, this is the column of expected frequencies, here and here. The column of expected frequencies has to equal the frequencies, the observed frequencies. Okay? Now, go back for a second. Notice the expected frequency here is only 0.25. The expected frequency of 1 is only 1.49. The expected frequency of 2 is 4.46. Now remember, in order for a goodness of fit test statistic, a chi-square test statistic, to follow the chi-square distribution, the expected frequency in every category has to be 5 or more. So what we're going to have to do is we're going to have to combine this. We're going to have to combine the 0 category, the 1 category, and the 2 category into 1 category. Now when we do that, the expected frequency is 4.46 plus 1.49 plus 0.025, which is at least 5. We're going to do the same thing down here. We have to add these 3 up because this is not 5, this is not 5, and this is not 5. So we have to create a category called 10 or more. So the observed frequency of 0, 1, or 2, the observed frequency is 5. How do we get to 5? Well, let's go back in time. See here, the observed frequency of 0 arrivals, 1 arrival, or 2 arrivals is 4 plus 1 plus 0, or 5. What about 10 or more? Where did the 10 come from? Notice 10 or more, we have 6, 3, and 1. 6 plus 3 plus 1 is 10. So this is 10 or more, 10, and 0, 1, or 2, the observed frequency is 5. 10, 14, 20, 12, 12, 9, and 8 are these frequencies here, 10, 14, 20, 12, 12, 9, and 8. Now we want to list the expected frequencies next to the observed frequencies. And we get 6.2, 8.92, yada, 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 all the way down to 8.39. Where does the 6.20 come from again? The 6.20 comes from adding 4.46, 1.49, and 0.25. Where does the 8.39 come from? Adding 4.13, 2.25, 2.01 gives us 8.39. The 8.92, 13.39, 13.06, 16.06, 13.77, 10.33, 6.88 are these values right here. Whoops, 6.88. Next, we compute the difference in the observed frequency and the expected frequency. Now notice, if the differences are very small, that means what we observe is really close to what we expect. So the closer the observed frequencies are to the expected frequencies, the smaller the chi-square stat's going to be, because there's very little difference between what we observe and what we expect. So 5 minus 6.20 is negative 1.20. 10 minus 8.92 is 1.08. Yada, yada, yada. Now notice the largest difference is when x equals 6 occurrences. The observed frequency is 12. The expected frequency is 16.06. So there's large differences when x is 5 and when x is 6. Next, we want to compute the test statistics. So what are we going to do? We're going to square those differences. Negative 1.20 squared, 1.08 squared, 1.61 squared. Where does the negative 1.20, 1.08, yada, 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 1.61s come from? We're squaring this number, squaring that number, squaring that number, squaring this 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 number, and squaring this number. Now before we add up these squared numbers, we have to divide this by 6.2, this by 8.92, yada, yada, yada. This squared divided by 8.39. So when we do that, we add those numbers up, we get 3.274. Now the next question is this number small or is this number large? To determine whether 3.274 is small or large, we have to compare it to a critical value in this chi-square table. Now, if these differences are very, very small, that means what we observe is really close to what we expect. So the smaller the chi-square stat is, the more evidence in support of the Poisson distribution. So with alpha equal 0.05, we're in column 0.05. We had 9 categories, right? 1, 2, 3, 4, 5, 6, 7, 8, 9 categories, with all the expected frequencies being 5 or more. So we have 9 categories. Now, all the probabilities were approximations because we don't know the true mean of the Poisson distribution. We had to use an estimate of the true mean of the distribution. Remember, the estimate of the mean of the Poisson distribution was computed using sample information. The 6 represents the estimated mean of the Poisson distribution. Suppose we knew the true distribution. Mean was 6. Then the value for P would be 0, because P is the number of estimated parameters that are used to fit the data to whatever distribution we're talking about. In the normal distribution, we use the mean. We use an estimate of the mean and the standard deviation, so P would be 2 for a goodness of fit test for a normal distribution. In the Poisson distribution, the mean and the variance are the same values. And we used an estimate, one estimate for the mean. which happened to be the same estimate for the variance, which is why this value is 1. So the degrees of freedom here are 7. So we go to row 7 of the chi-square table and column 0.05 of this chi-square table, and we get 14.067. Now, the distribution of a chi-square is this skewed distribution. It is not symmetric. With alpha equal 0.05, the upper tail is shaded red, and that area is 0.05. So we go to column 0.05 of the chi-square table. Now, the degrees of freedom are 7, so the mean of this distribution, the hump, is approximately at 7. So the chi-square critical value is 14.067. Now, as the chi-square stat falls in value and gets closer and closer and closer and closer to 0, what that means is the observed frequencies are getting closer to their expected values, which pulls the chi-square stat value down. So chi-square stat values that are close to 0 provide much evidence in support of the Poisson distribution, because the expected frequencies are close to what we observe, and the expected frequencies were computed using probabilities from the hypothesized Poisson probability function. If the chi-square stat is in the do not reject the null region, then what we're saying is it looks like the distribution of the data appears to be Poisson distributed. If the chi-square stat is up here, then the expected frequencies are a long ways away from what we observe, hence we don't have very strong evidence in support of Poisson. Now, the chi-square stat was 3.274, so we do what? We cannot reject the null hypothesis, which means there is no reason to doubt the assumption of a Poisson distribution.